So let's continue. Okay, we decided that we wanted to generalize all the beautiful stuff we saw in supersymmetric quantum mechanics to supersymmetric quantum field theories, but we wanted to know what we meant by that. Okay, so we want to know what the supersymmetry algebra might be in higher dimensions, and we had a sneak peek on that. The sneak peek told us that the supersymmetries would be spinors in higher dimensional spaces, and for that reason we started studying spinors of SO to n and SO to n plus 1. Okay, I'll remind you of the what we did. We had the Clifford algebra, which was gamma mu gamma nu is equal to 2 delta mu nu. We divided these gamma mu's into gamma a's and gamma a plus n's, which were defined in terms of these creation. Then we paired them up into pairs and made creation annihilation operators. And once we did that, we had that these guys were real and symmetric. We chose a basis such that these guys were real and symmetric. These guys were imaginary and antisymmetric. Okay. We had the matrix gamma 2n plus 1, which was equal to product I is equal to 1 to 2n, gamma I, let's make it A is equal to 1 to 2n, gamma A times I to the power n. This matrix was also real symmetric. I forgot to say that gamma mu's obeyed gamma mu dagger is equal to gamma mu. And because this is real and symmetric, the same was true for gamma 2n plus 1 as well. Okay. In the discussion section yesterday, in the class and then discussion section, we defined this matrix C, which is product gamma A is equal to 1 to n, gamma of n plus A. And we showed that C inverse gamma mu C was equal to minus 1 to the power n, gamma mu transpose. This worked for all these gamma mu's, but it also worked for gamma 2n plus 1. Okay. We now want to understand what the implications of this thing are. We also discussed that the representations of SOD. We also discussed the representations of the generator matrices of SOD. We discussed the matrices M mu nu is equal to gamma mu gamma nu by 4. And we explained that spinors have a lower index, gamma matrices have an index structure alpha beta, whereas the C matrix has index structure alpha beta. Okay? And in the discussion session yesterday, I started giving concrete meaning to the statement that C matrices have index structure alpha beta. And the concrete meaning was in terms of the transpose representation. So we discussed that it's a general fact that if M mu nu, if some matrices M mu nu give you a representation of an algebra, then minus M mu nu transpose also give you a representation of the algebra. And that representation is a simple representation. It's simply related to the original representation in the sense that it's the inverse representation, the original representation. In the sense that it's the representation of the object whose indices can contract with the original representation to give you singlets. Okay. So M mu nu transpose, which is equal to minus M mu nu transpose, which is gamma mu gamma nu by 4 transpose with a minus sign, which is equal to gamma mu transpose gamma nu transpose by 4. This was a representation. Okay. these generate the inverse representation of the spinors. Okay, any questions or comments? Otherwise, I proceed. Is there a minus sign in front of here? Yes. There's a minus sign here. And that minus sign goes away here because of the extra minus sign in the order of the commutator. Okay? Now, very quickly, let's look at a couple of things. The first thing I want to show you is that suppose chi transforms in the inverse representation. Then C chi, so this chi transforms in inverse. Then C chi transforms in the spinorial representation. So that's the claim. The claim is that if chi is an object that transforms in the inverse representation, C chi transforms in the spinorial representation. Okay? So what is that? In order to show this, what I have to show is the following. I want to compute delta of C chi. How this changes under an SOD transformation. Okay? But this quantity here is C doesn't change, of course. So it's C times delta of chi. But this is C times how this object transforms, how chi transforms under SOD, but by definition it transforms with this generator. Okay? So it's C times gamma mu gamma nu transpose by 4 with a minus sign. Gamma mu gamma nu transpose by 4 with a minus sign on chi, or which is the same thing as C times gamma mu transpose gamma nu transpose by 4 with a plus sign, as we've already seen. Okay? But now I take the C through the gammas. Now I take the C through the gammas, so I do that by rewriting this relationship as gamma mu is equal to C gamma mu transpose C inverse with a minus 1 to the power n, just by multiplying this side by C and this side by C inverse. Okay? So what that tells me is that if I take C through to gamma mu, through a gamma, it becomes a gamma transpose, it becomes a gamma up to a factor of minus 1 to the power n. But both these expressions have two gamma transposes, so the factors of minus 1 to the power n becomes minus 1 to the power 2n and becomes nothing. Okay? And so this is the same thing as gamma mu gamma nu by 4 on C chi, which is what we wanted to show. We wanted to show that C chi transforms exactly like an ordinary spinor does under rotations. Is this clear? It's the kind of manipulation we'll use very often. Okay? That tells you that a representation and its inverse are not really different things. If you've got something transforming in a representation, you can make the spinorial representation, you can manufacture the inverse representation, or vice versa, by multiplying by, it's just a basis change. Okay? And we found the basis change function, that's the C. This is the precise sense in which C has two lower indices. It's precisely an object that converts an upper index to a lower index. Okay? Because the guy within the inverse transformed in the upper index. Okay. Now now I want to explain to you. Okay. Now I want to explain to you that if I have a spinor chi, okay, I want to show you that chi star times C, where star means complex conjugate, also transforms like a spinor.
It has an upper index.
Chi itself has a lower index. chi itself is an ordinary spinor. Sorry, I maybe should have called it psi. Maybe that was the confusion. So I've got a spinor psi alpha. I take its complex conjugate and multiply by c. I'm going to now show you that that object transforms like an ordinary spinor. What does this mean? We know that c times something that transforms with the inverse representation transforms like an ordinary spinor. So effectively what I'm going to show you is that chi star transforms in the inverse representation. I mean, it's obvious, but let me just work out the algebra anyway. So suppose I take chi star. I now ask, how does this transform? Okay, so I want delta of chi star. Okay, so that is gamma mu star, gamma nu star by 4. Okay, so suppose I take delta of, sorry, I should have started with delta of c psi star. That's what I want to check. So that is gamma mu star, gamma nu star by 4 times the c times chi star. Is this clear? That's by definition. But we use now the fact that these gamma matrices are Hermitian. So gamma star is the same as gamma transpose. Okay, so this is gamma mu transpose, gamma nu transpose by 4 because of the hermiticity properties of the gamma matrix. And then the rest of the calculation is exact. Now we've reduced it to a solved problem, as mathematicians like to say. Okay, so this is the same thing as gamma mu, gamma nu by 4 on c chi star. And so we've demonstrated that c chi star also transforms like a spinor. Okay? So what is the general rule? The general rule is that if psi is a spinor, c psi star is also a spinor. Okay? Another way of saying it is that starring in SOD takes a lower index and makes it an upper index. Okay? Great. So far, we've been sort of fooling around. Okay, this is like some group theory and so on. Much of what I've said is, yeah. However, yes. Star does that thing. We've not seen anything else that does that. I mean, C, of course, lowers the index. But given psi, if you take psi star, that is something that transforms in the inverse representation. And then C can be used to lower it. Okay? So if I write psi, if I was very careful with notation, psi star should be written as psi star alpha. The index goes up. Okay? Now, let me focus for a moment on SO n2n plus 1, on the odd guy. The fact that psi and C psi star transform in the same representation suggests something. You see, if we're doing physics, you know, in representation theory, the difference between real and complex things is often not very important. But in physics, the difference between a real spinor and a complex spinor is all important. It tells you, it doubles the number of degrees of freedom. Okay? So if we've got a physical theory, if we have a spinor psi, and we want to work with the minimal number of degrees of freedom, we might want to impose the condition that it's a real spinor. Now, what does it mean for it to be a real spinor? That might be imposing the condition psi is equal to psi star, you might naively think. Except this equation is neither right nor wrong, it's just nonsense. Because the two different terms on the two different sides of the equation have different index structure. They transform differently under the SO to n plus 1 group. So this is not an equation you can impose. It just makes no sense. Yes? SO2n plus 1. I'm doing SO2n plus 1 at the moment. I'm including this guy. We'll come back to SO2n. There's no difference. You're saying no difference between upper and lower. That's what you're saying? That's true for vector indices. We're now talking about spinor indices. Okay? You know this is not, anyway, yeah. For instance, SO6 is the same as SU4.
Yeah.
And the spinor index of SO6 is a vector index of SU4. And you know that for SU4, there's a big difference between upper and lower indices.
So you have, more technically, you have gone into the spin group of...
Doubtless. Okay, yes. More technically, I'm working with the spin group. I shouldn't be calling it SO at all. But such subtleties are for mathematicians. Okay. Okay. Excellent. Let's move on. Fine. So this equation makes no sense, but now that we've done all this preparatory work, we have an equation that does make sense. Suppose I try to impose the condition psi is equal to C psi star. This is an equation that maybe either right, that maybe is nonsense, but is is more sophisticatedly nonsense than the earlier equation. Okay? The referee for your paper won't immediately catch it if he doesn't know about spinors, if it's nonsense. Okay. So, this is a first order plausible equation to impose because both sides transform the same way under SO2n plus 1. However, there's a second order consistency requirement. And the second order consistency requirement comes from the following manipulation. Look, if this is true, then I can complex conjugate this equation. So that must mean that psi star is equal to C star psi. From one follows the other. But now I can plug this back into here. And so I find that psi is equal to C star times psi. Now this equation is only consistent if C star is the kind of matrix that has eigenvalue 1. Otherwise that equation was still nonsense. Now let's figure out whether C star has eigenvalue 1. Okay, so we're going back to understand properties of this, to review properties of the C matrix. Let me quickly. Firstly, something that will be important that I haven't yet computed is what C transpose is. Okay, so let's first compute C. So now we're going to go and study the C matrix for 2 minutes. Let's look at C transpose. C transpose is equal to gamma 2n transpose gamma 2n minus 1 transpose up to gamma n plus 1 transpose by definition. And I just transpose the definition of C. Now, we know all of these guys were antisymmetric. So that is equal to minus 1 to the power n times gamma 2n gamma n plus 1. And now I want to reorder the gammas so they've come back in the order they're supposed to be in. The first reordering gives me a factor of minus 1 to the power n minus 1, next n minus 2, and so on. So we get minus 1 to the power n times minus 1 to the power n into n minus 1 by 2 times C. Is this clear? Okay. Which is equal to minus 1 to the power n into n plus 1 by 2 times C. That's great. Questions or comments about it? I'm probably going a little faster in this lecture, and you know, it's one of these accelerating trajectories. The next lecture will go super fast. Okay. But I hope it's still clear. You must stop me if it's not clear. Okay. Okay. Well, so now, why have I bothered with C transpose? I bothered with it because I can write, you know, this now as C dagger times this factor. Because transposing C picked up this additional, the dagger and star differ by transpose, and transpose picks up this additional factor. And now I see this is a positive definite operator, but this is a sign. Okay, 1 is a positive definite number. Okay, so if C dagger has to have eigenvalue 1. It's certainly impossible if this sign is negative. But it is plausible, and in fact, I won't show you, but it's true if the sign is positive. So this equation here, this equation that this integrability condition, that it is possible to satisfy this integrability condition, is the same as the condition that minus 1 to the power n into n plus 1 by 2 is positive. If and only if this condition is satisfied, can we consistently impose the condition psi is equal to c psi star. Okay? Now, this is all very nice. Actually, everything I've said here so far, everything I've said here so far worked both for SON plus 1 as well as SO2n plus 1 as well as SO2n. Okay. But let me stick, there's one more issue happening with SO2n, which we're going to come to in a minute. But so let me just stick to the odd guys. So let's see. Suppose n was 0. Okay, n is equal to 0. So that's SO1, let's say. Just nothing, but we'll see there's a periodicity. So, okay. Then, tick. What about SO3? That's n is equal to 1. No. SO5, that's n is equal to 2. 2, 3, no. Okay. SO7, that's n is equal to 3. Sorry? SO5 was n equals 2. Yeah. So n equals 3, this is also doesn't work, right? Because this is 4 by 2, so that's 2. Oh yeah, you're right, it works. It works. Yes, SO7. And what about SO9? Okay, so that there is n is equal to 4, so that's an even number, so that works. Now something you can convince yourself is that this quantity has periodicity of 4 in n, or of 8 in the dimensionality. Okay? So though we've computed it for SO1, SO3, SO5, SO7, now you can just repeat the whole thing. SO9 is the same as SO1, SO11 is the same as SO3, and so on. This is the periodicity that keeps going. Okay, so this table is sufficient with the periodicity to tell us about which dimensions real spinners are possible in, for which odd dimensions real spinners exist. Okay? Suppose we're not in one of these, suppose we're in one of these bad dimensions. We're looking at SO3 or SO5 or SO, what would it be, 11 or SO13. Okay? Then what kind of equation can we impose? The best we can do is this. Not have one spinner, but 2. Or an even number of spinners. Let's give the spinner some flavor index I. And then we can impose the condition, then it's possible to impose the condition psi is equal to, psi I is equal to omega ij, psi c, psi star j, where omega is any antisymmetric matrix. Because then in the squaring of this condition, we'll pick up a factor of this antisymmetric matrix squared. Okay, I'll choose a particular antisymmetric matrix. Let my antisymmetric matrix be 0, -1, 1, 0, 0, -1, 1, 0, and so on. This is a matrix that squares to -1. It's like it's like somehow getting an additional factor of -1 in this integrability condition here. Okay, so in the dimensions where you can't impose the condition psi is equal to c psi star, you can, if you have an even number of spinners, group them together to impose this kind of condition. Yes? You see, I doesn't help because we're doing c times c star. So suppose you multiply c with I, c star gets multiplied by -I. So it doesn't help. Thank you. Okay? Other questions or comments? Excellent. So, when you put a condition like this has a name. The condition of this form, when it's consistently imposed, is called a reality condition. And you say there are real spinors in this dimension. Okay? When you put a condition of this form, it's called a pseudo-reality condition. And you say that those dimensions have pseudo-real spinors. Is this clear? Any questions or comments? Okay, excellent. Now, so far, we have been dealing with the example of, what I forgot to talk about is chiralities. Let me quickly tell you about that. Now, the odd dimensions were good. But in even dimensions, we already saw that the spinor representations are actually reducible. They break up into the chiral and the anti-chiral representations. So another question that is important is this. Another question that's important is this. It is, if I take psi star of a chiral spinor, is it chiral or is it anti-chiral? That's another important question if we're in even dimensions. Everything I said here so far holds for even dimensions as well, but there's an additional question you could ask. So let's ask that question and answer it. Yes. It could be that the inverse representation of the chiral spinor is an anti-chiral self. Yes, this could happen. Okay? And this is the thing we're going to try to find out. Okay. Yes. So, yeah. So we did that fast. You see, first we were dealing with just one spinor. And we wanted to make it real. In the good dimensions, we could just do it, no problem. In the bad dimensions, we couldn't. Okay? So now we're looking to see what else we can do. So suppose instead of one spinor, we had two spinors. Let's take that as the example. Okay? And then once we do it with two, we can do it with 4 and 6 and 7. Okay? So suppose we had two spinors, so that this index I here, and this index I just tells me which of the two spinors. Psi1 is the first spinor, Psi2 is the second spinor. Okay? Then I can impose this condition consistently. Because when you do the squaring, you get a factor of this omega squared, which is -1, which cancels the -1 and the -1 to the power. Okay? So what you can do is if you had double the number of spinors, then you can impose some sort of reality type condition, but not one spinor by itself. Okay? Now if you can do it with 2, you can do it with 4. That's all that this omega ij does. Right? Thank you. They change. I'm going to tell you about it. Yes. Okay, but before we go to Lorentzian, let's quickly understand the chirality business. So the question that we're going to ask you now is, if I take C psi star, okay, and if psi was chiral, what is C psi star? That's the question. So that's very easy to answer. The fact that suppose psi was chiral, it means that psi was the same thing as 1 plus gamma to n plus 1 by 2 times chi. So if psi was chiral, this is equal to C into 1 plus gamma 2n plus 1 by 2 psi, the whole thing star, from the fact that psi was chiral. Right? But now, in an arbitrary basis, we would have to worry a lot about how to star this object. But you remember, our gamma 2n plus 1 is real. So we can just put the star entirely on this. Okay? And then we take this guy through here. Now, what do we get when we take gamma 2n plus 1 through C? Exactly. The answer is -1 to the n. Why? Because when gamma 2n plus 1 commutes with every gamma, anti-commutes with every gamma matrix. So if you took it through one gamma matrix, you get a factor of -1. But C is a product of n gamma matrices. So you get a factor of -1 to the power n. Okay? So this is equal to -1 to the power n. Sorry. 1 plus -1 to the power n gamma 2n plus 1 by 2 times C psi star. Okay? So, now we see that when n is even, n is 0, 2, 4, so on. Okay? When n is even, the complex conjugate of a chiral spinor is a chiral spinor. On the other hand, when n is odd, the complex conjugate of a chiral spinor is an anti-chiral spinor. Is this clear? Okay? Is this clear? Questions, comments? It's because there's no odd dimensions, there's only one kind of spinor. There's no chiral anti-chiral spinors. The question doesn't exist. Okay? So now you see that in even dimensions, let's list what we can say about the spinors. The reality properties of 0, 2, 4, 8 are the same as, 0, 2, 4, 6, 8 are the same as listed there. Since 0 sounds bad, we'll start with 2, 4, 6, 8. Again, there's a periodicity. So the reality properties were 2 was the same as 3, so that's pseudo-real. 4 was the same as 5, that's pseudo-real. 6 and 8 were real and real. Right? That discussion is unchanged. However, there is the question of whether a spinor is interchanged or not. Okay, so not interchanged, and interchanged I'll write as Ni. Okay? Not interchanged means complex conjugation takes a chiral spinor to chiral spinor. Okay? So we see here that this is n is equal to 1, so that's interchanged. N is equal to 2 is not interchanged. N is equal to 3 is interchanged. N is equal to 4 is not interchanged. Okay. So look at SO8. It's a beautiful dimension. In SO8, it's possible to have spinors that are real, and the reality condition does not interchange the chiral and the anti-chiral spinor. So it's possible to define a real chiral spinor. Okay? What about in SO4? Once again, the spinors are not interchanged. Did I get this? I messed up, right? No, sorry, I got it. Sorry. Sorry, that was right. You see, we computed here these reality properties that depended only on the symbol n. N was we used the same symbol n defines the properties of 2n plus 1 and SO2n. Okay, so whatever happens for an odd dimension happens for the immediate previous even dimension. Okay? And so now what do we get? In this dimension, the chiral spinors are not interchanged. So complex conjugation takes a chiral spinner to a chiral spinner. However, one can only impose a pseudo-reality condition on the chiral spinner. Okay? What about the other dimensions? In these dimensions, since the spinners are interchanged, complex conjugation doesn't take you back to the same representation. So the question of imposing a reality condition seems like a moot one. Okay? In those dimensions, we just say that the spinner representations are complex. So chiral spinner, complex conjugated, takes you a different representation. We'll just call those complex. It won't matter very much to us, real pseudo. Okay? Questions or comments before we proceed? Can you have a non-chiral real spinner in how many dimensions? This, yes, you can. Yes, you can. You see, right? You can. Okay. So, okay, excellent. Now, the last thing I want to do before moving on to the actual supersymmetry algebra is to generalize this discussion to SO. I'm using Stratid's notation 1, 2n minus 1, or SO 1, 2n. Namely, instead of being all Euclidean, one of the things is time. Okay, Lorentz space. Now, how much of our discussion changes? Actually, very little. You see, because it's a marvelous fact about these Clifford algebras that if you have a representation of SO 2n or 2n plus 1, and I want to take that to a representation of SO 1, 2n minus 1, all I have to do is to take gamma, what was, let's say, gamma 2n here, and multiply it by I. So let's define gamma 0 is equal to I times gamma 2n. And now a collection of gamma matrices is gammas from 1 to 2n minus 1 and gamma 0. A collection of gamma matrices is the same as the collection we had before, except one of our gamma matrices has been multiplied by I. Okay? In this case, now our gamma matrix algebra is gamma mu is equal to 2 eta mu nu. As you can easily check, right? The gamma 0 squared picks up an additional factor of I squared. That makes the difference between delta and eta. Okay? Now, all we've done is take one of the gammas and multiply by I. Everything we said about transpositions is independent of a number behind a matrix. A matrix is symmetric or not symmetric, independent of what you multiply it by, whether that thing is I or minus I or whatever. So everything that we said about C, the C matrix, goes through without a change. Okay, so the C matrix for SO2n minus 1, for this case, is the same as the C matrix for the Euclidean thing. And we get the same algebra. Okay, so once again, we have, whether you want to put an additional factor of I in the C matrix or not is up to you. It makes no difference. So you might want to now define the C matrix as gamma n plus 1, gamma n plus 2 times gamma 0. You can do it with that or with an I. The reality properties of C had no. C star was important, but not any independent number of C. In what? In transposition of C? No, nothing changes. Okay? It was never important to us whether C was real or imaginary. Okay? But it's up to you. If you want, you can even multiply it by I. It doesn't matter. Okay? So when we do this now, when we do this now, everything we said about C remains unchanged. So once again, we have the formula C inverse gamma mu C is equal to minus 1 to the power n times gamma mu transpose. This remains true. Once again, we have the formula C transpose is equal to whatever it was. Minus 1 to the power, what was it, n into n plus 1 by 2. C remains true. Okay? What has changed at all? You might think nothing's changed. But actually something has changed. And let's look at what has changed. What has changed is the Hermiticity conditions. By the way, just to record, not that we're going to use it, gamma 0 is antisymmetric and real in our basis. Because gamma 2n was antisymmetric and imaginary. Okay. Yes? Yes, it works the same in both cases. Okay. Let me add one more comment related to that. You could ask, what about gamma 2n plus 1? So gamma 2n plus 1 is now, actually as a matrix it is unchanged. But as a product of gamma matrices it picks up an additional I. So gamma 2n plus 1, okay, is now product A is equal to 1 to 2n, gamma, let's say 2n minus 1, gamma A times gamma 0, if you want to write it this way, then we will write it as I to the power n minus 1. Why? Because we need gamma 2n plus 1 to square to 1. The old matrix did it, so we'll keep it the old matrix. But the old matrix had an I to the power n. Okay? And the old matrix had an I to the power n, and this gamma 0, okay, I suppose with my conventions, plus 1. Okay? Gamma 0 is an additional factor of I. How did I get it to the other way? Is it plus 1 minus 1? Sorry. Let's see. So gamma 0 is minus 1. So, yeah, it removes the extra factor. You want to remove the extra factor of I. Thank you. Minus 1. You could define gamma 5, gamma 2n plus 1 with 2 minus gamma 2n plus 1. That's entirely a matter of convention. It makes no difference. Okay? But this quantity here is this, and it remains true now that gamma 2n plus 1 is equal to real, symmetric, and Hermitian. Is this clear? Questions, comments? Okay. So once I say this, you know, everything for SO2n 2n plus 1 also goes through. Okay. The one thing that is different is the Hermiticity property. So we previously had that gamma mu dagger was equal to gamma mu. Now this is clearly not true anymore, because gamma 2n dagger was gamma dagger, gamma 0 dagger is minus gamma 0. Now how do we write that in a way that looks sort of nice? That's a nice way to write it. It is that gamma mu times gamma 0 inverse gamma 0 is equal to minus gamma mu dagger. Let's check. If gamma mu is one of the non-gamma zeros, you take gamma 0 through, pick up a minus sign, and then we get 1 here. So that works. That gives gamma mu as gamma mu dagger. If gamma 0 is one of the gamma zeros, I mean, gamma mu is gamma 0, then you take this through without a penalty in sign, and you get gamma 0 is minus gamma 0 dagger. So that works. Okay? So the Hermiticity condition is more complicated here. And because of that, the statement that if chi is a spinor, chi star transforms in the inverse representation is no longer true. Because you remember we used for that the gammas obeyed, gamma mu is gamma mu dagger. However, there's a simple replacement for that statement. The simple replacement for that statement is that if psi alpha is a spinor, then gamma c times gamma 0 psi star transforms like a spinor. Is the statement clear? Okay, let's check this. In order to check this, all we have to do is to see how this guy transforms. So we want to compute delta of this. Okay, so to compute delta of this, that's the same as computing delta C gamma 0 times delta of psi star. So that is C gamma 0 gamma mu star gamma nu star by 4 psi star. Is this clear? But taking gamma 0 through this up to a minus sign, okay, taking gamma 0 through here up to a minus sign turns this into the dagger. Or I could put it on this side and make it fine. In this expression, yeah, you're absolutely right. You just take gamma 0 through, and that turns it into dagger up to a minus sign. But the minus sign doesn't matter because there are two of them. Okay, so this becomes C times gamma mu transpose gamma nu transpose by 4 psi star. Is this clear? And now we have reduced it, like our friends like to say, to a solved problem. What? You're right. Now we take the C through, that gets rid of the transposes, and so we have gamma mu gamma nu by 4 C gamma 0 psi star. And so C gamma 0 psi star transforms exactly like psi did. Is this clear? Of course, in some language you know all of this in 4 dimensions. Multiplying by gamma 0 is the bar operation. That's why when we deal with Dirac spinors, we like the quantity psi bar better than we like the quantity psi dagger. Because psi bar transforms in the inverse representation to psi, whereas psi dagger does not. Right? So, that's all I'm saying. I'm saying that this quantity is psi bar, transforms in the inverse representation, and then I lower the index using C. Clear? Now, okay. So now that we understand this, we have to analyze reality properties of spinors in Lorentzian space. Okay? Why do we have to do this reanalysis? We have to do this reanalysis because we have to impose a different potential reality condition. We cannot impose the condition psi is equal to C psi star. Makes no sense, because the two sides don't transform the same way under the Lorentz group. But we can impose the condition, we can try to impose the condition, psi is equal to C gamma 0 psi star. At least this is first order sensible because the two sides transform the same way under the Lorentz algebra. Under SO, this SOD, whatever. Is this clear? So this is the putative thing that we're going to try to impose. But now we'll take the star of this. So that's C star gamma 0 star psi. But let's look here. Gamma 0 was real in our basis. So gamma 0 star is gamma 0. Okay. Plug this back in. We get psi is equal to C gamma 0, C star gamma 0 psi. Whether you put a star there or not doesn't matter. And this condition is consistent if and only if this quantity here admits a +1 eigenvalue. Okay. Now, what do we get when we take gamma 0 through this quantity through the C. Let's be careful about this. You might be tempted to say that you get a minus 1 to the n, but that's not right because one of the gamma matrices in C is gamma 0 itself. So you get a factor of minus 1 to the power n minus 1. And then we get a factor of gamma 0 squared, which is another minus 1. So this is the same thing as C star times minus 1 to the power n. Is this clear? Now, we already checked, C hasn't changed, we already checked that this quantity is equal to C dagger into minus 1 to the power n into n plus 1 by 2 into minus 1 to the power n. And so, this is the same as C dagger into minus 1 into the power n into n minus 1 by 2. Is this clear? So, when real spinor rather than pseudo-real spinor representations exist or not in SO 2n minus 1 comma 1 or SO 2n comma 1 is determined by whether this number is plus 1 or minus 1. Is this clear? Excellent. So now we can make our favorite tables. Why? Was there a question? You could not read? You want me to move here? Sure. Yeah, you. This one? Minus. This is minus. Okay. So let's work first in odd dimensions. So D is equal to, let's say, 3 is equal to 5 is equal to 7 is equal to 9. Okay. Now we have to do complicated algebra. So here n is equal to 1, so that gives 0, so real. N is equal to 2, so that's 1, so pseudo-real. N is equal to 3, so that's 2 into 3, so that's pseudo-real. Right, n is equal to 3 is 2 with 3, fine. And what about 9? N is equal to 4, so that's real. Is this clear? Okay, great. Great. The last thing that we have to do in order to complete our listing for even dimensions, the last thing that we have to do is to redo the analysis of whether the complex conjugate of a chiral spinor is chiral or not. Okay, so let's quickly redo that analysis. So, suppose we've got a chiral spinor. We want to understand what happens to C gamma 0 times psi. But because it's chiral, this is the same as psi star. Same as C gamma 0 times 1 plus gamma 2n plus 1 by 2 psi star, where I've used that gamma 2n plus 1 is real. Okay. Now I have to take this through these guys. But you see, the difference is that in addition to taking it through C, I have to take it through an additional gamma 0. So I pick up one extra factor of minus 1. So I get 1 plus minus 1 to the power n plus 1 gamma 2n plus 1 by 2 on C gamma 0 psi star. We get the opposite conclusion from Euclidean space. We find that a chiral spinor, the complex conjugate of a chiral spinor is chiral. Okay? If n is odd. But the complex conjugate of a chiral spinor is antichiral if n is even. And so we are now now we can write our table for even dimensions. Okay. So write our table now for even dimensions. Okay. So let's do D is equal to 2, 4, 6, 8, 10. I don't really need the 10, it's same as 2, but because 10 is an important dimension, I'll write it separately anyway. Okay. Fine. So what had we found? D is equal to 2 is the same as for reality properties, we'll just write that down. Pseudo-real, pseudo-real, real. No, yeah, right. Real and also real. And so it keeps going. Okay. But when is it interchanged and not interchanged? D is equal to 2 is n is equal to 1. So that's not interchanged. And then it just alternates. So interchanged, not interchanged, interchanged, not interchanged. So in which Lorentzian dimensions do you have real chiral spinors? We have real chiral spinors in D is equal to 2. And then periodically with 8. D is equal to 10, D is equal to 18, and so on. Okay. What about in D is equal to 4? The spinors are interchanged, so the spinors are complex. Nothing more to say. What about D is equal to 6? The spinors are pseudo-real, but not interchanged. So you cannot impose, in D equals 6, you can't impose a reality condition. But you can impose a pseudo-reality condition of the sort that we had before. Okay? So it will be psi is equal to omega ij, psi I is equal to omega ij, C gamma 0 psi star j. That's the kind of condition you can impose. Okay? And chiral spinors remain, you can impose them separately on chiral spinors and anti-chiral spinors. D equals 8, complex. D equals 10. That's another good dimension. Spinors are real and not interchanged. So you can consistently define real chiral spinors in 10 dimensions. Something we use all the time in string theory. Actually, we use these facts all the time in string theory. Here we use it on the world sheet of the string, here we use it in spacetime. Okay, excellent. Questions or comments? Yes? Interchange and complex means the following. What does it mean that it's interchanged? It means that this quantity, if I take a chiral spinor and do C gamma 0, if I take C gamma 0 psi star of a chiral spinor, the resultant is antichiral. So this operation on the chiral spinor, we complex conjugate a chiral spinor and multiply it by this stuff. You get a spinor, but not a chiral spinor, an antichiral spinor. So you can't equate the original chiral spinor to that object because it just doesn't transform the same representation of the Lorentz algebra. So complex conjugation, you see, a fundamental fact of representation theory is, the fundamental question is, does complex conjugation give you the same representation or a different representation? If it gives you the same representation, then you can try to impose a condition that the original, that with some linear transformation, the complex conjugation is a linear transform of the original guy. Okay? And that may or may not be possible. That's what we've been analyzing. But of course, if the complex conjugate is in a different representation, then you're done from the beginning. There's no hope of imposing anything. Okay? So interchange means complex conjugation takes a chiral spinor to an anti-chiral spinor. So there's no hope on a chiral spinor of imposing a reality condition. Do you understand? Okay. Other questions, comments? Other space-time signatures are very similar. You just have to do the same analysis. I haven't done it actually. In fact, it's of interest to the conformal algebra because the conformal algebra is SO D, 2. And so this is an interesting question. It's very similar, but you know, you may have noticed here that 10 dimensions here behaves very similar to 8 dimensions for the Euclidean algebra. Okay, and the general rule, if I remember right, is that SO d minus n times n, the reality conditions are the same as SO of d minus 2n. Let's check that this is working right here. So SO 9.1 would be the same as SO 8, which is correct. I think this is the general rule. Say again, please. The what signature? SODD, I suppose, is same as SO 0. What does that mean? Okay, firstly, I won't swear by this rule, okay? I think I remember this. I'm not 100% sure it's right. I think it's right, though. We could probably figure it out. Because it would just be putting... I think this rule is right, and what it means for SODD, I don't know. Okay, that sounds like an ill-defined rule for SODD. I would have to think about that. But let me just continue because I want to write down the super. Good question. Yes? Well, a Majorana spinner is a real spinner. That's what Majorana means. There are Majorana spinners, but they're linear combinations of plus chirality and minus chirality. You can't have a real Majorana chiral spinner. So you can impose a reality condition. It's just that you have to mix chiral and antichiral. Okay? So let's say we're interested in irreducible representations. For irreducible representations, you can ask, okay, can you cut down the number of components in an irreducible representation by making it real? That's the question we're asking. Okay, great. Now that we have all this preparation, we come to the thing that we wanted to do, namely to write down potential supersymmetry algebra, in fact, the real supersymmetry. The many checks, I will only write it down and perform simple checks for you. Supersymmetry algebras in arbitrary numbers of dimensions. Actually, the algebra, go on. Yes. Yes. Every even dimensions you can write down wild spinners. All this is talking about is the properties of these spinners under complex conjugation. The existence of these spinners was just manifest because gamma 2n plus 1 was there. Anti-commuting with everything. All gammas and therefore commuting with the representation matrix. Is this clear? Yes. Okay, it means that, see, this is not going to be of importance to us, but it means that you can combine together a single real, a single chiral spinner and an anti-chiral spinner together to make it a real, whatever, full component spinner. Okay, you take the chiral spinner, which you add together its complex conjugate, and you can make that whole thing real. You can make that whole thing satisfy this condition. However, it's not a very important statement. Because you see, the reason we wanted to impose that condition was to cut down the number of components. Okay, and we're not cutting down the number of components. We're just taking basically. Let me say it again. Let me say it again. Maybe I should say it this way. Suppose I take a complex spinner. Okay? Then its complex conjugate is the other chirality. So the degrees of freedom you have to deal with is a complex chiral spinner. Okay? And then noting that it is equal to something else is not very useful. It's not giving you a cut down in degrees of freedom. Okay? So it's not, for our purposes, a useful statement. the object you have to deal with is a complex chiral spinner, which you can also view as a complex antichiral spinner. Because its complex conjugate is a complex antichiral spinner. And then the reality condition is not going to be important to us. Okay, let's move on. Now, I want to write down the supersymmetry algebra. And the supersymmetry algebra, because of the properties of spinors change in different dimensions, the supersymmetry algebra itself changes in different dimensions. Okay, its details are different in different dimensions. But it has the same periodicity as the property of spinors, namely periodicity mod 8. So, I'm going to write it down just in the interest of time. I think I'll do d equals 2, 3, 4, 5, 6. Because we're going to be studying the rest of these lectures, whatever's left of them. We're going to be studying quantum field theories. And let's hurry up. Yeah. Let's first do 2. D is equal to 2. This is the same as 10, right? Okay. In this space-time, we have real chiral spinners. Okay. So we have real chiral spinners. So we could have, I told you that supersymmetries were going to be spinners. But now we have a choice. They could be chiral spinners or anti-chiral spinners, or we could have both. So let's suppose our superchargers there are n plus chiral supercharges. Okay, and q j alpha, so I is equal to, j is equal to 1 to n minus anti-chiral supercharges. Okay, these numbers define the supersymmetry algebra. They'll become. Can you read this? So suppose we've got q plus I alpha, which are the chiral supersymmetries, and q minus alpha j. This is a different index. You know, it's an anti-chiral index. I won't distinguish, but one should. Maybe maybe I should put something like this. Okay. I'll mess up, so I won't distinguish, but it should be a different index. In d equals 2, but say we d equals 10. So when I say 2, I mean 2, 10, 18. So let's write it as 10, because 2 is too trivial. Okay, excellent. Now, I is equal to 1 to n plus, and this j here is equal to 1 to n minus. Okay, I have to choose n plus and n minus. Theory with so many supersymmetries, so many chiral supersymmetries, n plus chiral supersymmetries, and n minus chiral supersymmetries. Different choices of n plus and n minus give us different supersymmetry algebras. Okay. Alpha is a chiral spin index, and this alpha is an anti-chiral spin index. Okay. Now the supersymmetry algebra takes this form. Suppose I have to specify various things for you. I have to specify q I alpha, q j alpha. This anti-commutator. Beta, it's called. Plus. Okay. Now, this is, I'm going to write this as gamma slash C. P slash C. Where P is the momentum operator. Okay. Q minus alpha, Q minus beta. Okay. This quantity good, thank you. This comes with the delta Ij. Okay. That is in here. Okay. this has an alpha beta. Okay? Similarly, Q minus alpha, Q minus beta is equal to P slash C, alpha beta delta, let's call this Mn, Mn, and Q plus I, alpha, I hope I've got it right. Let me just check I've not interchanged. If you want here, we can put here 1 plus gamma 2n plus 1 by 2. To emphasize this was chiral, we can put here 1 minus gamma 2n plus 1 by 2. And the last element in this algebra is Q plus I alpha, Q minus J beta. This quantity is Zij. This quantity is Zij times C alpha beta. So I'm sorry I've written so haphazardly. In the equals 10, this, and this line together make up the supersymmetric algebra. Is this clear? Okay, so what we have is the chiral spinors, roughly speaking, squared to give you momentum. The antichiral supercharges, also roughly speaking, squared to give you momentum. And the chiral and antichiral supercharges can obey an anti-commutation relation with each other with this Zij. Now let's look at a couple of things. When you have an expression like this, somebody's written it down to you, you may or may not be able to derive it, but you can immediately subject it to various consistency checks. So one consistency check you can subject it to is the following. Look, this anti-commutator here goes to itself if you interchange alpha, beta, and I and j. Okay? Here, interchanging I and j is just doing nothing. Okay? Interchanging alpha, beta is taking transpose of the right-hand side. Okay? So, this algebra only makes sense if this whole thing transposed is itself. I'll leave it as an exercise for you to check that this is the case. Okay? It's a trivial exercise actually, but I'll leave it as an exercise for you to check that this is the case. Okay, we have all the information we need. You know what C transpose is, you know everything. Okay? See, you just check that this is the case. Moreover, this algebra here has a chiral spinor with a chiral spinor. Now, chiral spinor, when you act with 1 gamma 2n plus 1 on the left, back itself. So if on the left-hand side, if I act 1 plus gamma 2n plus 1 by 2, I should get back the left-hand side. Therefore, I should get back the right-hand side. That's manifest here. But what if I acted on the right? What if I acted with this thing on the right? There, once again, I should get back. I should get back the chiral spinor, right? Because gamma 2n plus 1 was its own transpose. It acted the same way from left and right. Okay. So if I act with this with 1 plus gamma 2n plus 1 by 2 on the right, I should get back the same thing. That means I should be able to take this through here. I should be able to take this through here. And it should be 1 plus gamma 2n plus 1 by 2, which squares back to itself. It's a projection operator. This is also true and it's also quite trivial to show. But you guys know everything about the C's and everything about everything. So you can just check all these things. Okay? So the algebras I've written down for you are subject to various consistency checks, which now you have all the information to check. And since we don't have all the time to check, I won't check for you. Okay? But you can do it yourself. Is this clear? Yes? What is this object you're asking? Well, this transforms like the product of chiral and an anti-chiral spin. No, nothing like that. The C alpha beta has the right properties for it to be, yeah. That, anyway, I won't go through all of this. I won't say more just in the interest of time. But right. There's much more you can say about convincing yourself that all these things are correct. For instance, here, there's a consistency check. There's no consistency check about transposition because this object and this object are different. But there is a consistency check about 1 plus gamma 5 by 2. Okay. So this quantity here, if you want, you can put a 1 plus gamma 2n plus 1 by 2 on the left. But that should be the same thing as putting a 1 minus gamma 2n plus 2 on the right, because the index for the second index is an antichiral index. So this must mean that if you take 1 plus gamma 2n plus 1 by 2 through a C, you get 1 minus gamma 2n plus 1 by 2. And you can check that this is all these consistency checks you can do, and they all come out right. Okay? So this, in 2, 10, 18 dimensions, is the generalization of the supersymmetry algebra that we saw for quantum mechanics to field theory. You see that it preserves Lorentz invariance because of P slash. Okay. Now, what is Zij? Okay, Zij is some number that can take any value. Let's first look at the situation where Zij is equal to 0. You can ask, what Zij have to be antisymmetric in I and J. Not in this case, because Q plus and Q minus are completely different things. The antisymmetry or symmetry would be forced by looking at the antisymmetry or symmetry of the left-hand side. Okay? No. But one of them is a plus, the other is a minus. So whatever manipulation you do, you'll never... In fact, I and J can run over different numbers of values. So it makes no sense even for it to be antisymmetric. It's just some arbitrary thing. Okay. Yep. So very quickly, if Zij was 0, then you see that this algebra has what people sometimes call an automorphism. That is, there is a symmetry transformation you can do on Qs, such that under the symmetry transformation, the algebra does not change. What is the symmetry transformation? Remember that Qs are real chiral spinors. So the symmetry transformation you can do here is the symmetric transformation of real linear combinations of Qs that leave the delta Ij invariant. But that is just SON plus times SON minus. Okay? So the outer optomorphism algebra, I believe it's called something. The algebra of operations you can do on Qs, linear transformations you can do on Qs that leaves the algebra unchanged, is SON n plus times SON minus. With Zij non-zero, that symmetry is broken. Or another way of saying it is that Zij transforms like a bifundamental under that symmetry. It's a number that maps you to another number that transforms like a bifundamental. Okay? Let me very quickly write down the other dimensions. Let's at least get to this point. Okay. So let me write down so now suppose D is equal to 311. Okay. Now we can go here. In D is equal to 3, we had real spinors. So we just have one kind of spinor, it's Q alpha, so it's very simple supersymmetry algebra. You have Q alpha I, Q j beta. I'll take like 5 minutes extra. I'll just write down all these algebras, organizer, that's okay. Yeah, alpha I, Q j beta is equal to P slash C alpha beta delta Ij plus Zij C alpha beta. Okay. Now you can check. Once again, you can perform consistency. Let's look at this term first. You can perform all the consistency checks I told you about last time on that term. Symmetry. Now, okay, not all of them because there's no chirality. They can perform the symmetry consistency check. Yeah, similar kind of check. What about this term? Now we come to the question that you asked. You see, this quantity here is symmetric under interchange of both alpha, beta and ij. This quantity C, let us remember, so we have to remember, C transpose was equal to minus 1 to the power n into n plus 1 by 2. Now we're in d equals 3, that's like n is equal to 1. So this is odd. So C is antisymmetric. Okay, therefore Zij must be antisymmetric under interchange of ij. What is the automorphism symmetry of the algebra? What is the symmetry of linear transformations on Q's that you can do that leave the algebra unchanged? Well, this I and j run from 1 to n. And the automorphism symmetry is SON because Q's are real. This Zij transforms like an antisymmetric tensor under SON. Is this clear? What? Everything's Minkowski. No, the transpose did not care about Euclidean or Minkowski. It's that dagger thing that did. Okay? Yeah. We have the SON only with Z equals 0. And if Z is non-zero, then it's broken by an adjoint valued field of SON, by an antisymmetric tensor of SON. So that it's restored if you allow Z also to transform under SON. Okay, great. Now let's do D equals 4. In this dimension, let's go and look. In this dimension, we had interchange spinors. Because we had interchange spinors, our spinors are just complex guys, which can all be taken to be positive chirality. They're complex, so they're complex conjugate negative chirality. Doesn't matter. So we have that whole spinor. So what we have to do is to give the supersymmetry algebra for Q plus alpha, the commutation relations of Q plus alpha with itself, and Q plus and alpha with the complex conjugate. Okay. So let's take Q plus alpha I, Q plus, I'll call this beta bar J. So I'll take the, star and multiply by gamma 0. So that the spinor index goes up. Okay? This quantity is simply P slash. No C now. Alpha beta. The commutation relation Q alpha, Q beta, Ij. Okay. This can be equal to Zij, C alpha beta. D is equal to 4, 12, and so on. This is the algebra. Now, what? Delta Ij, thank you. Now, let's look at this. I'm ignoring the consistency checks. Let's quickly look. What is the automorphism algebra? Here, the Q's were complex. So you're allowed to perform complex linear combination of Q's. Okay? It has to leave this delta Ij invariant. So that gives you Un. So the automorphism algebra is Un, where I is equal to what? To n. Okay, what about the Zij here? Well, once again, the whole thing has to be symmetric under interchange of both these guys. What about C alpha beta? In this case, once again, we use this formula here, where in the case n is equal to 2. Once again, it picks up a minus sign. And so Zij is antisymmetric. These Z's have a name, by the way, they're called central charges. Okay. Now, yes. Q minus is just the, you see, there's no Q minus, or another way of saying Q star is Q minus. So if you want the relationships of Q star with itself, just complex conjugate this object. That gives you the answers. No, bar is star times gamma 0. Okay? So I'm not writing down what you get for complex conjugates, because you just find it out by complex conjugating this. Okay? And then you can, if you want, you can multiply with gamma zeros. Wherever you get is what you get. Okay. Let's now do d equals 5. Okay. D equals 5. Well, it had the same properties as d equals 4. So it's pseudo-real. There's no question about interchange. So now it's going to be a little bit like this three-dimensional algebra. However, it's pseudo-real. So we've got Q alpha I, Q beta j. Okay? This quantity is equal to omega ij. Okay? Omega ij p slash c alpha beta plus zij c alpha beta. Where omega was the matrix that imposed the reality condition. Is this clear? Okay. Once again, there are many things to check. Here, you see, you need an omega rather than anything else. Firstly, it's natural. But secondly, the symmetry property would not have worked. This quantity, rather than being symmetric under alpha beta interchange in this dimension, is antisymmetric. So if you combine it with the antisymmetry of omega ij, that makes it all work. Okay? And what about the symmetry of C alpha beta? Well, we're in D equals 5. So N is equal to 2. So 3, 2, still antisymmetric. So this guy, once again, is antisymmetric. Okay. And the automorphism is SO. No, S now. The automorphism is SPN. Because of the omega. Because we want linear combinations that preserve omega. Okay? And the last one I'll write down is D is equal to 6. D is equal to 6. The spinors are not interchanged, but they're pseudo-real. Okay? So what does the algebra look like? We have Q plus I alpha, Q minus I beta, Q plus I beta, Q plus I alpha, Q minus I beta is equal to omega ij, P slash C alpha beta, Q minus I alpha, Q minus J beta. Okay, this runs from 1 to n plus. This runs from 1 to n minus. Okay, is equal to omega, let's call this Mn. Mn P slash C alpha beta. Okay, and Q plus I alpha, Q minus N, let's say M beta, is equal to Zmn C alpha beta. Where Zmn has no particular symmetry properties. The automorphism algebra in this case is Spn plus times Spn minus. The two omegas are different because one acts on an n plus times n plus dimensional space, the other is in an n minus times n minus dimensional space. In the SPs, you're right. SP. Well, you know, it depends on your conventions. for SP. There's a approximately even distribution of conventions, whether that's called SPN or SP2N. But I'm happy to go with your conventions. Okay. What? Yes, thank you. What? Then D equals 5. Maybe we use different conventions in different dimensions. Okay. There should be an even number of charges, but whether the thing, the thing whose fundamental representation is 2n dimensional, whether that's called SP2n or SPN is according to taste. Right, so, fine. Right, but yeah, you're absolutely right. That, right, fine. Okay, I need to stop here. I need to stop here, so I'll stop here. Okay. What about 7, 8, and 9? Just, it's very similar. So work them out as an exercise. Okay. I've just not done it because will not be of relevance to quantum field theory, but it follows a pattern you could quite easily generalize. Yes. Automorphism group is what we know as R symmetry. R symmetry is something I should emphasize. A theory that has the supersymmetry algebra may or may not, a quantum field theory that implements supersymmetry may or may not implement the R symmetry. It's not inconsistent for a theory to implement supersymmetry and not implement the R symmetry. R symmetry is just an additional symmetry that the theory may have, which interchanges the Qs, but it's not compulsory. However, once the supersymmetric theories are enhanced to have superconformal invariance, turns out that the R symmetry appears on the right-hand side of the commutation relations. And then the algebra would be inconsistent unless the theory implemented the R symmetry. So there is this hierarchy of R symmetry is sort of like a curiosity for theories that implement supersymmetry, but an essential feature of theories that have the superconformal algebra. I was planning to talk about all of this, but I don't think I'm going to have the time. I wanted also to discuss at least one non-trivial dynamical phenomenon in supersymmetry, namely the IR behavior of supersymmetric QCD, the arbitrary numbers of flavors. So that's what I wanted to do next time. I suppose that's what I'll do next time. I'll give you maybe 5 or 10 minutes in words about other things I was going to say, and then we talk about that. Yeah. Ask questions. Yes.